we're going to talk about probability. So probabilities and statistics go hand in hand. You have to have one in order to study the other. So probability is the chance that an event occurs. And probability is the basis of inferential statistics. So if we are going to help predict something that's going to happen, make an inference based upon the data we have collected, that's where probability is going to help us. So the first section of Chapter 4 is about sample spaces and probability. What is probability? How do we use it? How do we determine what possibilities might occur so that we can find their probabilities? We're going to talk about what a sample space is, finding that basic probability. Now, most people are exposed to probability in their lives. What are the chances when you roll a dice of rolling an even number? We understand what those concepts are. Well, we're going to take that in Chapter 4, talk about those introductory things, and then we're going to expand upon it even further in Chapter 5. So some basic things that you're going to have to know for probability. A probability experiment is something like flipping a coin, rolling a dice, picking a card. Now, those are very simplistic things, and those things are going to help us to understand the concepts more in depth, because things like that are unusual in real life. There's usually many more possibilities than that. There's many different variables working together. But by understanding these simple ones, we'll be understanding probability to a much higher level later on. So we'll start with the little stuff, and then we'll work our way up to more intricate stuff. Now, a probability experiment is a chance process that leads to well-defined results called outcomes. Let's go back to rolling the dice. What is my outcome if I roll a standard six-face die? Well, my outcomes are rolling a 1, rolling a 2, rolling a 3, 4, 5, or 6. That's an outcome. We have well-defined results. Those are our outcomes. Flipping a coin. The results are heads or tails. So, and a probability experiment is when we take and look at the chance that something will occur. So again, an outcome is a result of a single trial of a probability experiment. So if I look at my coins, one outcome is flipping a heads. One outcome is flipping a tails. There are two outcomes within that situation. Rolling a die. One outcome is getting a 1. One outcome is getting a 2. And 3, 4, 5, and 6 are all the outcomes. A trial means flipping the coin once and seeing what happens. Rolling the die once. Answering a multiple choice question with 4 options where maybe we have a random selection generator that randomly picks the answer. If we sit there and flip the coin 60 times, we have done 60 trials. If we roll the dice 50 times, we have executed 50 trials. The more trials you do, the more chances that you're going to really see in the long run what might happen, depending on what circumstance you're dealing with. So what kind of outcomes we get? Well, I've mentioned them before. When we toss a coin, the two outcomes are heads or tails. Multiple choice questions might be A, B, C, or D. So the outcomes are what are the possibilities of the things that might occur, and that you have to include all the possibilities. And then a trial means, hey, you try that thing and you see what comes out. A sample space is a set of all possible outcomes. Now the key here is the word all. You must include all possible outcomes for it to be a sample space. You can't forget any. So if you had a multiple choice question that had A, B, C, or D, and you said the sample space was only A, B, and C, that's incorrect. You have to include all the possible outcomes, so it's A, B, C, or D. Now, the more things you add in, the more outcomes you might have. So if I say flipping a penny and a dime and seeing what my outcomes will be, that changes things compared to just flipping one coin. So you have to take into consideration all the possible outcomes that should be in your sample space. So the experiment would be to toss a coin. Your sample space is heads or tails. Rolling a die, sample space 1, 2, 3, 4, 5, 6. Answering a true-false question, true and false are your sample space. Tossing two coins. Now here's where it gets a little more in depth. Let's see if I can get this a little bigger for you. If we toss two coins, you can get heads on both, tails on both. The first one has a head and the second one has a tail, or the first one has a tail and the second one has a head. There's technically 4 different possibilities in our sample space. Now, some sample spaces are just by reasoning and logic. Some sample spaces you have to actually observe to see what's going to happen. We're going to try to have to organize these data. Just like when we first were getting data from chapters 1, 2, and 3, that we took the data and then we organized it somehow. Well, if we take and look at our sample space, really keeping it organized, the more things we have in it, the more chances that we are not going to miss a certain outcome in all the possibilities. So I'm going to show you how to make some different charts and trees and the things that they're talking about here, so we can kind of organize our thoughts. Now, when you probably were exposed to this somewhere in like 8th or 9th grade, I would assume, maybe, during that time you probably made something called a tree diagram. So we're going to mess with that so that you can see that, just so we can get different ways to organize and kind of think through what our different outcomes could possibly be. So let's look at an example. So the question is to find the sample space for rolling 2 standard 6-sided die. So we just have the 1, 2, 3, 4, 5, 6. And what are our possibilities of our sample space? Well, think about the fact that each die can land 6 different ways when 2 dice are rolled. The sample space can be shown in what's called an array. So here's one chance. So look what happens. If I got 1 on the first and 1 on the second, that gets me to it. That's the 0.11. 1 on the first, 2 on the second. That's the 0.12. So that little array shows all the possibilities for die 1 across the top, die 2 across the top, and all possibilities for die 1 across the side. And then we just sample them up, kind of join them up. So here's this right here is if I got 4 on the first die and 2 on the second die. 5 on the first die, 6 on the second die. By organizing like this, we can see all the possibilities very clearly, and we're less likely to forget one. If you just start trying to write it down, all the possibilities, you might forget one. Usually you can come up with a pattern of what's happening in that, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, or 1, 6. And then 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. You can come up with that pattern. There are actually 36 different elements in this sample space. The array just helps us organize the data so we don't leave any out, we don't forget one, we don't repeat something that we shouldn't have repeated. Do you see how there were 6 possibilities on the first die and 6 possibilities on the second die, and we got 36 things? 6 times 6, 36. That's not by coincidence. So because if you flip a coin and then do a die, the coin has 2 possibilities, the die has 6 possibilities, you're going to get 12 different options. So we're going to talk about all that. Let's talk now about flipping coins. So there's an array. Let me show you a very, very simplistic tree diagram, okay? A coin flip. This represents the first coin. Can either be head or tails. And then the second coin can either be heads or tails, for the original being heads or tails if the first one was tails. Let me show you how you can interpret that. This means heads first, then followed by head, heads then tails, tails then head, tails then tails. Do you see how the bottom has 4 ending positions? That means there are 4 outcomes. So you count really the branches, the final level of branches on the tree. There are 4 branches. 1, 2, 3, 4 branches. That means there are 4 outcomes. So this is kind of indicating the possibilities for the first flip, and this is the second. So tree diagrams are perfectly acceptable. Yes? Is this what if you're just flipping one coin twice? Yes, exactly. So you're flipping a coin once, and then you flip it again. Yep. And if you did it a third time, it would branch out, and now you would have 2 branches for each of those. So instead of just having 4 outcomes, you'd have 8 outcomes. And if you did it 4 times, you'd have 16 outcomes, and it would keep building on itself. So there's a coin flip. Here's an example. Find the sample space for the gender of 3 children in a family. So we're just thinking traditional birth genders. And it says, in a family of 3 children, find the sample space for the birth order of gender of their children. What are the possibilities that this family could have when they give birth to children? Well, if the first child is born, you're either going to get a boy or a girl. Okay? That's a B and a G. Let me make them bigger. This is B.
Oh, I love it.
Okay. So that's the first child. Then the second child could either be a boy or a girl. And then the third child could either be a boy or a girl. And let me just write the outcomes out here. So how many different possible outcomes could occur? 8, right? Because think about, first it was 2, then it doubled again, now it's 4, now it doubled again, now it's 8. So there are 8 possible outcomes. How many of those outcomes result in having all boys? So 1, right? How many of those outcomes result in having 2 boys? 2, right? This one is 2 boys. Oh no, 3. This one is 2 boys. This one is 2 boys. What are the chances of having no boys? 1 out of the 8, right? Just that bottom one. That's the only one that has no boy in it. It's all 3 girls. Okay? So we're going to use that thought process that is kind of just instinctual to help us. You'll notice that organizing it in this little tree diagram sort of thing is helpful. If you don't like it going to the right, you can adjust things for saving space. I went to the right, but okay. So that's the sample space. That BBB, BBG, BGB, that's your sample space. And you could write out the words, but you don't have to. Just some kind of abbreviation is fine by me. Now, an event consists of a set of outcomes of a probability experiment. So the event of them having 3 children had all of those outcome possibilities. So we had the boy, 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 girl, boy, all those different possibilities. An event can be just one outcome, or it can be more than one outcome. If there is only one outcome, it is called a simple event. Let's scooch this down so you can see it better. If it has more than one outcome, we call it a compound event. So flipping the die was a compound event. The genders of the 3 children, compound event. Rolling the die, compound event. Most events have more than one possibility. There are three interpretations that you want to think about of probability. There's classical probability, and that's what you usually start out with when it comes to the probability of rolling a 1 on a die. So that's your classical probability. That's more of what most students start with, is that classical probability. Empirical or relative frequency probability, we are going to talk about. I think that's chapter 5. So we're going to build upon. Chapter 4 is mostly your classical probability, and then we're going to work our way up to the empirical or relative frequency probabilities. Subjective probability is not something we can do at this level too much. Subjective means you are making a prediction. You can make a prediction, but as far as making a knowledgeable prediction, then that comes with more upper level statistics that we will probably not get too much of in this class, a little bit, but not as much as you would in like a mathematical stats and probability class. So let's talk about what the differences are. We're going to start with classical probability. Classical probability uses sample spaces to determine the numerical probability that an event will happen. The events of what's going to happen, what are my chances of flipping a heads or tails? What are the chances if I have 3 children of getting 2 of them that are boys? Stuff like that. We use those sample spaces. We look at how many occur of the things we want and how many occurs of the things we don't want, and then that leads us to that classical probability. We assume that all outcomes are equally likely. So we're assuming that it's very simplistic, that my chances of getting a boy are the same as my chances of getting a girl. Now, in real life, is it like that? No, not completely. But you'll see families where they had 5 children, they were all girls, or 5 children, they were all boys. So it's not usually completely that cut and dry. But for our purposes, if we're dealing with classical probability, you're either going to get a girl or you're going to get a boy. We're not going to overthink it. You either get a heads or you get a tails. We're not going to really overthink the other chances that and the other variables that come into play, because there are other things that, of course, can happen. So here's a formula you're going to need. If a sample space has n equally likely outcomes and an event A has k outcomes, then the classical probability of event A is. Now, I'm going to read that of the probability of A or P of A, and I'm going to write this a little bigger. That means the probability of A. So the probability of me having 2 boys, the probability of me flipping a heads, the probability of me getting a 5 when I roll a die. So the A is the description of the event that you're trying to get. So the K is the number of things that are the things you want, event A. So if I want to have boys, that would be how many of those things had a B in there. The number of outcomes N is how many things were in the sample space. So for like flipping a coin twice, we had 4 things in the sample space. So that N would be 4. For the gender breakdown of having 3 children, that was 8 different possibilities. Our N would be 8. So it's just how many different outcomes. And again, for simplicity's sake, we're going to assume that each outcome is equally likely. For a die, you can cheat, and you can make it so that the die tends to land on the number 2. You might have heard loaded die or weighted die, and because it isn't a fair die. So we're assuming, for our purposes, that each chance is just as likely as happening. So let's look at an example. Now we're going back to that 3 children, and it says, what is the probability that all 3 children are of the same gender? Well, if you looked at our list, so I typed out the list for you here. There were 8 outcomes. There were only 2 on that list where the children all have the same gender. So if we think about our probability, the probability to have 3 children of the same gender, that would be the number that have the same gender over the total possibilities. Okay, and I don't think that's the way you spell possibilities, but I can never spell. 2 S's, yeah. Like if somebody said, hey, you must spell this word right, or we are going to, I don't know, chop off your leg, I would really be in trouble. So what do we got? Well, 2, that's the number of possibilities where all the kids had the same gender, 3 boys or 3 girls, and there were 8 total possibilities. So it would be 2 8s, 2 out of 8. Sometimes you'll read it 2 out of 8. That tends to somewhat be language you use for odds a little more than probability, but you can say 2 out of 8. That's fine by me. Then any type of fractional answer that you get, you should take the time to reduce it. Those are both divisible by 2, so please reduce it to 1/4. Decimals aren't completely helpful in some mathematics. For probability, you see decimals quite often. So if you gave me a decimal value of 0.25, I'm okay with that as well. Decimals are going to be something that you'll see in probability quite a bit. Sometimes even you'll change that to 25%, but most of the time you're going to keep it a fraction or decimal. So let's look at some rules. There are 4 main characteristics that you need to know. We're going to use these to solve probability problems. Just understand what the numbers are going to be telling us and deciding whether the answers are correct or not. So if you know these 4 things, it will help you just understand these concepts a little better. So let's start with the first thing you should know. The probability of an event occurring is always some number between 0 and 1. The probability of an event occurring is always something between 0 and 1. If you get a probability answer of 1.6, rethink what you did. You did something wrong. The probability of an event occurring is either 0% or 100%. If you think of it like that, it's either 100% chance occurring, there's not a 200% chance. Okay? So it's going to be between 0 and 1. The sum of the probabilities of all the outcomes in a sample space is 1. Now, let me prove it to you. If I flip a coin, the probability of me getting heads just once, just flipping it once, the probability of me getting heads is 1/2. The probability of me getting tails is 1/2. Add those 2 up. What do you get? 1. Because all the possibilities should encompass 100% of everything that is possible. So if you think of it almost as the possibilities instead of the probabilities, those words can loosely be kind of exchanged for each other in your brain. Next, if an event A cannot occur, so if I say to you, what is the possibility of rolling a 7 for a standard die? Can that ever occur? No. So that probability is 0. So if an event cannot occur, the probability of it occurring, we say, is 0. Now, if an event must happen or is certain to happen, then the probability of it is 1. What is the probability that you're going to be sitting in this class today? 1. You're already here. It's already happened. Okay? So when we're talking about something that must or is certain to happen, the probability of that is 1. So the probability of me flipping on a standard coin, a heads or a tails, is 1, because that's every possibility. So this little chart I saw and found, and I thought it was just really helpful. Okay, and maybe I'll put it on another page here in a second once everybody gets caught up. But the way that you want to think about it is if you're in the center, if your probability is 0.5, you got a 50-50 chance of getting it. So like a heads on a coin flip. I have a 50-50 shot of flipping a heads. And what was the probability? 0.5, 1/2. The closer we get to 1, the more likely we are getting. So if you get a probability of 0.8, 0.9, you know it's, hey, that's getting really close to possibly just happening. The closer we get to 0, 0.2, 0.1, the less likely that thing will occur. So the smaller the decimal is, the closer it is to 0, the less likely it's going to occur. The higher it is closest to 1, the more likely it's going to occur. So that little chart I think was just, just a really good way to kind of put it and see where the probabilities would fall. So let's look at some more examples. Probability of rolling a die. Consider we have a standard fair die. It's not weighted one way or the other. All the outcomes are just as likely as happening. I can roll a 1, 2, 3, 4, 5, or 6. What is the probability of rolling a 5? Well, how many are 5s on the die? 1. And how many possibilities do we have? 6, right? And so the probability of the first one is 1 out of 6. The probability of me getting a 5 on the first roll is 1 out of 6. Now, I listed out the sample space there to remind you, well, how many things are possible? 6 things are possible. So in this particular one, my K was 1. Only one of them is a 5. My N is 6. So my probability of getting a 5 is 1 out of 6. Now let's read the second one. Find the probability of rolling a multiple of 3. So then you got to think, okay, what are multiples of 3? 3, what's the next one? 6, what's the next one? 9. So if you look at our list and you have it listed out, you can find them really quick. That's a multiple of 3, and that's a multiple of 3. So what's our K? How many are things that we want? 2, right? How many total possibilities were there? 6. And so our probability for that would be 2 out of 6. Now, the probability of rolling a multiple of 3 was 2 out of 6. Get in the habit of reducing that. I really don't like decimals too often for this, because those are those decimals that can keep going and going and going. So if you give me an exact fraction, just stop. Just reduce it. So those are both divisible by 2, make it 1/3. So then if you think about it in just a logical sense, 1/3 of all the numbers on that list were multiples of 3. So one thing that's really interesting, and I think we explored here in a minute, is what is the probability of me not getting a multiple of 3? Well, yeah, there are 4 numbers out of 6 that are not a multiple of 3. 4, 6 plus 6, 6, or plus 2, 6, I'm sorry. Isn't that 6, 6, or 1? All the possibilities. You're either getting a multiple of 3 or you're not. That's all the possibilities. Okay. Let me make this. Here's another example. Find the probability of rolling an 8 when rolling a standard fare die. Exactly. We've got. If you look at that sample space from before, our possibilities are 1, 2, 3, 4, 5, and 6. Is 8 on that list? Nope. So that is a 0. Remember, if there's no chance of it occurring, the probability is 0. You can also think about it as the probability of getting an 8. I have 0 8s. I have 6 total things. So that's why it's 0. I don't have that. That's not a possibility. Something that is going to happen. Find the probability of rolling a value less than 7. Think about our sample space. 1, 2, 3, 4, 5, 6. The probability of getting a number less than 7. Well, how many of those are what we want? 6. How many things are there on the list? 6. That's why it's 1. Because it's all the outcomes. All the outcomes should always give you a probability of 1. Now, if you take one outcome out, like if we ignore the 1, it lowers that probability and it's something less than 1. But if all the possibilities are included, you should always get 1 or you did something weird. Now, there are times where you will denote something. Gosh, when I transferred this over, it did weird things. Just a minute. There's a little bar it's not there. There we go. Let's put that where it belongs. Okay. We can talk about the complement of an event. Okay. Earlier I said to you, what were the chances of us not getting a multiple of 3? Well, I did that on purpose because a not, thinking of the things that are not what you want, is called a complement. A complement of event is the set of all the outcomes that are not included in what you want. Okay? We denote it with a little bar on top. So in the homework, if they say the probability of A, that is all the things that include an A. But if they have a little bar on top, that is all the things that are not A. And sometimes instead of A bar, I'll just, for my own brain purposes and to help you memorize what that means, I'll say not A. Because that reminds you that it's everything that is not A. But A bar or not A, they're both okay. If the probability of an event or the probability of its complement is known, then the probability of the other can be found by subtracting the known probability from 1. Remember how we got, I'll flip right back to this, but remember how I mentioned how the probability of getting a multiple of 3 was 2 out of 6, and the probability of not was 4 out of 6, and they're always apart by 1. Or if you add them up, you get 1. So the rule is, if you know the complement, subtract 1 and you know the original's outcome. If you know the original's outcome, subtract 1 and you know the complement. So there's 3 things that can happen. The complement, that does have a little bar on top, is 1 minus the original. Or the original is 1 minus the complement. That has a little bar on it. That's a bar. That's a bar. Or the addition of the original probability plus the probability of the complement will always equal 1. So if they say, what is the probability of not getting something? If you know the probability that it takes to get that thing, just subtract it from 1 and you'll get what it's not. So it's just kind of a shortcut. If you've already calculated 1 and they want the not of it or the opposite of it, you just subtract it from 1. So just know that notation means not A. And if you're good at algebra, you only need one of those bottom formulas and you can always solve for the missing thing. If you're not good at algebra, write all 3 down. So let's look at some examples of where this not could be asked. So it says find the complement of each event. So event A, select a day of the week that begins with a T. So first, how many days of the week start with a T? 2. So the probability of A is 2 out of 7. Now they wanted us to find the complement of that. So the probability of the complement of that is just 1 take away 2 sevenths, or 5 out of 7. Doesn't it make sense? 5 of the other days of the week do not start in T. Okay? So Sunday, Monday, Wednesday, Friday, and Saturday do not start with a T. Okay? So that's why it's 5 out of 7. Now, obviously, you could have just figured that out. I have 5 things. I count Monday, Wednesday. But I wanted to show you mathematically why it works. Let's take a look at event B. 2 dice are rolled. You want to get a sum that is odd, a sum that is 3, 5, 7, 9, or 11. So you're adding up however many. What are those little dots called on a die? There's a name for them. Pills? No, I don't know. There's a name for them. Dots on the die. Okay. So let's think. If I roll 1, 1, that sums up to 2. 1, 2. Well, I did the work for you. You can really add up from 2 to 12. That's all the possibilities. You're either going to add up to 2 through 12. How many of those possibilities are the event we want? How many are odd? Well, wouldn't you agree that's 3, 5, 7, 9, and 11. There's 1, 2, 3, 4, 5 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Now, without counting the other ones, let me prove it to you. The probability of not getting an odd should be 1 minus 5 out of 11, which is 11 11s minus 5 11s, or what plus 5 gives me 11? 6 out of 11. Count the evens on the list. 2, 4, 6, 8, 10, 12. 6 out of the 11. My not A and B don't look very good, do they? The little knot line did not move where it should. That should have a little knot in it, and that should have a little knot in it. Okay. These ones are so tiny that you can count the ones that are not even or not odd. You can count up the evens. But this just gives you an example. If you had a large sample space and you've already calculated the 1 probability, you can just subtract it from 1 and you find the probability of it not occurring. Now let's talk about something called empirical probability. Empirical probability relies on actual experience or observation to determine the likelihood of outcomes. So instead of just for the coin, heads or tails, this relies on us actually doing some type of experiment or observation and flipping coins. Okay. So it says, given a frequency distribution, how many times something happened, the empirical probability of an event being in a given class is the frequency of the things in that class divided by the total frequency in the distribution. Now this seems almost exactly like the other one, because in a way it is. It's the same idea. Here's the difference. You have set up some type of experiment, whether it's sitting there and flipping the coin yourself, rolling the die yourself, all the different things that you can actually observe to figure out what the probabilities are. We might find that the coin wasn't fair, and as we flip it, we tend to keep getting heads. We tend to keep getting tails, or whatever. So empirical probability relies on the unreliableness of real-life events. They don't always turn out exactly the way that you think. So let's look at an example with that. So we have surveyed 50 people, and we were looking at their blood type. All we asked about these people is, hey, what's your blood type? 22 of them were type A, 5 of them B, 2 of them AB, and 21 of them is O. So we have gathered this information. It's not exactly, but it's somewhat like a sample versus an entire population. We have sampled a part of the population and asked them what their blood type is. So it's more of like a sample versus an entire everyone. So it says, using the frequency table, let's find the probabilities that they've asked for. The probability that a person has type O. So how many did we find had type O? 21. Out of how many total? 50. So it's just 21 out of 50. Now, if that can reduce, reduce it. If it doesn't, leave it alone. Just leave it right there. 21 out of 50 doesn't reduce. If you wanted to make it a decimal value, you can. The probability, again, with those decimal values is you might have to round it a little bit. What is the probability that someone has either type A or type AB? So you see how we have to take type A or type AB are the things I want. I want a total of 24 outcomes out of the 50. So now it's 24 out of 50, because you got to add those two things together. Those are what's called mutually exclusive. You either are type A or you're type AB. You can't be both, and so you just add them up. Now that is a fraction that reduces. They are both divisible by 2. 12 out of 25. The decimal can somewhat be helpful, but not completely. I like sometimes, unless I have to do something with it, just leaving it 12 over 25. But if you gave me a decimal value, probabilities usually tend to go 3 or 4 decimal places, and we'll play with that when we actually get ones that are more decimal related. Now let's look at this one. A person has neither type A nor AB. So now we are looking at all the other places. Now I want to do it twice, okay? Isn't this really, if we call this probability of x, isn't this x bar or not x? Isn't the opposite? So one way we could do this is 1 minus 12 over 25, which is 13 out of 25. Now let's go back to our list for a minute. Is it 13? Yeah. I debated my subtraction skills there for a second. Let's go back to our list. We do not want type A. We do not want type AB. How many's left? 26 out of 50, which is 13 out of 25. Okay. So you can calculate it two different ways. You can realize that you've already calculated its complement and just take it off of 1, or you can physically take those things off the list that you do not want. Any questions about example 4.8? So far, so good? We just have a few more slides and then we're done for today. Let's look at this one. Now, the law of large numbers is important when you're dealing with probabilities where you are performing some type of trial. And it basically says that as the number of trials of a random experiment increases, then what's interesting is that the empirical probability will approach the classical or theoretical probability. Now what that means is, let's go as simple as heads and tails. We got a fair coin. We have somebody sitting there and they do 5 trials. You might get 3 heads and 2 tails. That doesn't seem 50-50, does it? But if you do 100 trials, you're going to get closer and closer to being 50-50. If you do 1,000 trials, you're getting even closer to 50-50. If you do 1,000,000 trials, you're even closer. So what it means is as we do this experiment, the more often we do it, the more numbers we get, the more it will approach that classic probability as if it was a fair, balanced coin. If it was a fair, balanced coin to begin. So sample size is important. If we do, trials are important. If we only do 4 trials compared to 50 trials, it will affect our outcome. So when you read over that term paper project, and it talks about looking at somebody at the fast food restaurant's total bill, you don't want to get just 10. You want to get more than that. Okay. So, suppose a fair die is tossed. The classical probability that we're going to get a 1, a 2, a 3, a 4, a 5, or 6 is 1 out of 6, 1/6. For an experiment that uses a fair die, as the number of tosses that result in a 2 increases, the closer we're getting to that 1/6. So that's just kind of what I said with the heads and the tails. If the die is tossed 1,000 times and we don't get pretty close to 1/6, there's something wrong with the die. The die they can, back when craps was just played out on the street somewhere, they might shave off a side so it tends to roll on a 7 or a 5 or whatever they want it to roll on. Okay, so a fair die, you can even weight them certain ways. So a fair die means I have just as much of a chance of rolling a 1 as I do a 2, a 3, or 4, or 5, or 6. So something's wrong with the thing that you are using, the die, the flipped coin, the experiment, if you don't start getting toward that 1/6. And our last thing, subjective probability. Subjective probability is not something that we will do much because it relies on the fact that we have some type of expertise in a field. Now, it will help us make informed decisions about some of the data that we're going to collect. But it's really based upon educated guesses. So we're talking about a weather forecast. A sports writer saying, I'm going to predict that the Browns are going to win. The Browns are going to lose. Whatever the case may be, okay? So it is more of a prediction based upon the knowledge that someone has in that field. I predict that over half of you will pass your test. Because I've been giving these people tests for a long time. It's the same sort of thing. I can make a prediction based upon my knowledge. That's a subjective probability. Now, some people will collect this data and see, well, how often is that forecasting right? Well, maybe channel 21 has a higher percentage of getting it right than channel 27, so I'm going to watch 21 weather instead of 27. This sportscaster, well, he gets it right most of the time. His predictions are right most of the time, so he's a little more reliable than sportscaster B that doesn't. So subjective probability is not something that we can do much in this class. Yes, you can make a prediction of what you think is going to happen and back it up with some data, but we're not going to do a lot of subjective probability just because it's not necessarily something we can do. Okay? So we're going to stop here for 4.1. Remember Thursday, what's Thursday? No, Tuesday. Thursday's your quiz. Tuesday, if you have any questions on homework 2 or 3, bring those questions on Tuesday, because that's when I can answer your questions to make sure you're ready for the quiz on Thursday. Thursday, let's try to get started and start the quiz right away. But if you have a few questions right before, we can do that too. So I will see you on Tuesday. We'll continue where we left off.